In this video, we will learn about electrocyclic reactions. Electrocyclic reactions are a subclass of pericyclic reactions in which overall we lose a pi bond and gain a sigma bond if it's a ring closing reaction, and in the opposite direction, if you're doing a ring opening reaction, you're going to be losing a pi bond and gaining a sigma bond. The way that we can categorize electrocyclic reactions is to divide them up by the number of electrons that are involved and also the type of rotation by which the process takes place. And so specifically the terms here are that the process can be either conrotatory, in other words that the carbons that are rotating the same way, or the electrocyclic process can be disrotatory, or again, those carbons that are rotating are going in opposite ways. And when I'm saying the same way or opposite way, what I mean is that in conrotatory, we're going to be rotating both clockwise or both counterclockwise, and in disrotatory, one carbon will be going clockwise and the other one will be going counterclockwise. So let's look at a couple examples to try to visualize this conrotatory and disrotatory process. So the first one here is a 4-electron conrotatory ring opening. You'll notice that I wrote 4 pi here, and that 4 pi is related to the number of pi electrons in the open form. Often students will get confused because they look at this molecule and say there's only 2 pi electrons. Well, we really care about the total number of electrons of the process, not just the number of pi electrons in this form of the molecule. So mechanistically what's happening is we're getting something that looks like this. And that's that ring opening. And if you're looking at the carbons that are rotating, those would be the carbons that I'm highlighting in red here. And that's where we want to focus our attention when it comes to this conrotatory and disrotatory process. So here, the way that I think about this is that both of these methyl groups are pointed upwards in my drawing, and they're going to be like windshield wipers and both rotating kind of in the same way, right? So I'm going to go both in one kind of either clockwise or counterclockwise direction. In my drawing here, I'm showing you with these red arrows that this is a clockwise type of rotation. And you'll notice how I drew my arrows like this, where I did like a half arrow there and a half arrow there. What I've noticed over the years is that when students draw things like that, it gets very confusing to them for whatever reason, whether or not that's clockwise or counterclockwise. So it is valuable to draw it out like this. So I have on the screen the model of this reaction. And if we're looking at it there, you can kind of see the 4-membered cyclobutene ring. And I have the 2 green atoms there pretending to be methyl groups. So that's going to match the drawing where I've highlighted in green. I'm going to highlight the 2 carbons that we are looking at when it comes to this conrotation that's going on. So that's those 2 carbons there. And if I take you through this animation of the reaction, you should be able to see that with respect to the entire molecule, we're getting those 2 green methyl groups kind of going clockwise toward the right a little bit. Now let's look at a disrotatory process. So I'm going to take here the 6-electron disrotatory ring closing process that's shown in this reaction right here. So if we're looking at our molecule that I have in the model here, you can kind of see that these end alkenes here are both trans, so the 2 large groups are going in opposite directions around that alkene. And if we're disrotatory now, our groups are going to be going like this. So let me draw it like this for you. So I'm kind of visualizing my 2 methyl groups kind of pointed out and then rotating in like this. That can also be drawn in my kind of more organized arrows like so, where this is the clockwise rotation and the other one is the counterclockwise rotation. In this reaction, you should end up with this product right here. I'm showing it to you with both of those methyl groups being wedged, but of course if you went the other direction, they would both be hashed, and actually that's the exact same molecule. Let me run through this animation as well. So we're going to take a side view here to try to see that disrotatory process. So if we're looking at that, you can kind of see how those methyl groups come together a bit and thus end up being both wedged. Right? So definitely in the 3D model, it's a little bit less kind of exaggerated because that's not how molecules actually move. But again, we're seeing those 2 methyl groups going from both pointed away from each other toward the left and the right and then kind of coming in together vertically. Of course, being a type of pericyclic reaction, an electrocyclic reaction will follow a set of selection rules, the Woodward-Hoffman selection rules. And in the same way as the other types of pericyclic reactions, we're going to categorize our processes by the number of electrons that are involved, and also whether that reaction is taking place under thermal or photochemical conditions. Turns out the combination of those two factors leads us to either requiring a disrotatory process or requiring a conrotatory process. Let's look at the frontier molecular orbital analysis for a couple examples here. The way that we'll do this is to take the opened form of the molecule, so the one with more pi bonds in it, and to look at the HOMO of that pi system. So in this case, this is essentially a butadiene, 4 atoms, 2 pi bonds. And if we're looking at the HOMO under thermal conditions, we should be looking at the pi 2 molecular orbital. So I have that all kind of drawn out here for you. And before going back to this table, we can just kind of look at this drawing on the right here. So I know I'm going from right to left. But if you look at it, the ends of that pi system have orbitals that are phased, or the orbital has components that are phased in opposite directions. And what that means is that my rotation of those 2 carbons has to happen in a way that puts the same phases together to create the sigma bond if I'm going from right to left. And conversely, I need to rotate these kind of broken apart sp3 type of atomic orbitals here. I have to rotate them in a way that gets me to the correct opposite phasing directions on the ends of the pi system if I'm going from left to right. So let me show you this in a physical model because I think it's much easier to appreciate what's going on when you're looking at a physical model. Here I have the blue chlorines on the ends of my carbons, and I'm not showing you any of the other atoms, just the 2 end atoms there. And so if you're looking at this and trying to see how these ends rotate to get the correct orbital overlap, I think you can appreciate that I can do this type of a rotation, and that then I'm required to do that rotation. And if you're paying attention, I did both of those clockwise, and so that's a conrotatory process. So that's what's required by the pi molecular orbital of this molecule. So then going back to our Woodward-Hoffman selection rules, we can see quite clearly that this all makes sense. We have a thermal reaction, we have a total of 4 electrons, and indeed, that's what our selection rules say. We are doing a conrotatory process. And so my point is that this is determined from all of this information here. You can also go the other way. So if I reset my molecule here, it is also totally valid to go counterclockwise and counterclockwise, getting you to that type of a sigma bond. You'll notice, if you pay attention, that the chlorines now are pointed in opposite directions in that ring closing process. So you're basically forming either enantiomer. I showed you the ring closing here, but of course the ring opening is the same thing. I can rotate counterclockwise and counterclockwise. In this case, I'm doing it in a way that put these 2 chlorines inside, which we'll get to later as to whether or not that's a good idea. So now let's look at the case where we're doing a disrotatory process. So exact same reaction, except we are under photochemical conditions. And if that's the case, then we should go to the opposite process. So we're still at 4 electrons, but now we're disrotatory. So if we're looking at our molecule, so I'm looking at our pi system here, what we see is that those ends should be aligned. So maybe let me set up my molecule correctly here. So really we're in this type of an arrangement in my physical model. And now if you're looking at it, if I want to mix my ends in a way that gets the phases, the like phases together, then I have to do it with opposite rotations. So if the left carbon is going clockwise, the right carbon has to go counterclockwise in order to form that sigma bond. And kind of the same idea, if I'm doing the ring opening reaction and I'm trying to get the ends of the pi system that I'm making to have their orbitals phase the same direction, I have to, let's say, do the counterclockwise for the left carbon and the clockwise rotation for the right carbon. And so that's why this is disrotatory. Again, all of this is decided or kind of predetermined by the Woodward-Hoffman rules, which all derives from these molecular orbitals. And so the outcome of this is that you'll notice that the reactions are stereospecific. Only specific isomers are able to be formed because these rotations are happening only in a certain way. A question that may have come up at this point is, well, when we do a conrotatory or a disrotatory process, there's actually a choice that we can make within those processes. So if we're doing a conrotatory electrocyclic reaction, that process can take place either both clockwise or both counterclockwise at those carbon ends. And so a natural follow-up should be, well, is there a reason to choose one over the other? It turns out the answer is yes, but only in some cases. What happens is that in a ring-opening electrocyclic process particularly, we see what's called torco-selectivity. It's best to look at this through an example. So let's take this molecule right here and do a conrotatory ring-opening process under thermal conditions. Well, we have that choice. We can either do both clockwise, I'm showing that in red here, or both counterclockwise, shown in orange. The clockwise process gets you to this product here, and the counterclockwise process gets you to this product here. So those are two stereoisomers of the same kind of structural formula. So looking at these two products, I think you can appreciate that this one must be pretty high in energy, and we want to be a little bit careful to note that it's not the fact that the product itself is high in energy that's the issue. The problem is that during the transition state from here to there, we are having to go through a very high energy transition state because the red clockwise conrotatory process brings the methyl group and the ethyl group into each other, right? And that's unavoidable. Even though the product, if we made it, could kind of conformationally change and separate those two large groups away from each other, the transition state itself is unavoidably going to have those be sterically clashing. So then the process that is more likely to happen, just from a kinetic point of view, is the both counterclockwise conrotatory ring opening, and that's what we end up seeing. The reason this doesn't matter as much in ring closing reactions is that in a ring closing reaction, we end up actually just forming enantiomers, and actually we are reducing the amount of steric clash when we're ring opening, because our real steric problem is between these two carbons here at the ends, right? It's the groups in the middle that are sterically clashing, and electrocyclic reactions actually take those and move them apart. So we're not that worried about sterics there. So this example reaction is the same as the one up here. We're just taking the product and going in reverse. So we can do either both clockwise or both counterclockwise. And if we go both clockwise, we should end up getting the first product here, the first enantiomer, and if we both go counterclockwise, we're going to get the other enantiomer. So again, a good place for you to check and make sure you can visualize what these conrotatory and disrotatory processes are doing to make sure that they match up with your product. I wanted to end here just by looking at a few interesting examples of electrocyclic reactions that have some historical importance. The first one we're going to look at is the electrocyclic ring closing of 1,2,4 Triter-Butyl benzene. And this should seem rather strange that you can do this type of a process, but it turns out that you can, under photochemical conditions, get this electrocyclic ring closing reaction. You might ask, well, if we're going from an aromatic ring to this highly strained fused cyclobutene product, how can that be energetically favorable? Well, it turns out that having two tert-butyl groups ortho to each other is actually highly unstable because of the steric clash that happens in between these two groups. And that's destabilizing enough to get us to being able to do this electrocyclic ring closing reaction. In the product, you see these fused rings here, so two cyclobutenes fused together. Turns out that if you just take that set of atoms there, the structure that you have has a chemical formula of C6H6, and that's the same thing as benzene. And when benzene was first discovered, this was actually one of the proposed structures for benzene, because people knew that it was C6H6, but they did not know whether those atoms were bonded in a ring, in a chain, or whatever, right? So because of that, then there was some scientific interest in trying to figure out, is this structure even possible? You know now that this is not benzene, but back in the day, people didn't know whether or not it was benzene, and even when they figured out what benzene was, there was still a curiosity of, can you make this, and what happens to it when you do? This reaction right here was the first kind of proof of principle that it was possible, and it took another set of researchers to go through all of this and eventually figure out a different pathway in which they did still a ring closing reaction to get to a molecule like this one, but then took advantage of a lead-assisted kind of an elimination type of reaction to get to Dewar benzene. What is maybe surprising here is that Dewar benzene is a strangely stable compound. If you just leave it in the dark, and just leave it in your vial, leave it in the dark, it will persist for days, if not weeks, before very slowly isomerizing into benzene. And so the key point here is that this has to be under complete exclusion of light. And so that should give you some hint that there's maybe a Woodward-Hoffmann type of a process or selection rule taking place here. And so if you take a look at this reaction, if you're doing the 4-electron Conrotatory ring opening, the 2 hydrogens that are at the bridge end up as these 2 hydrogens here. Those have to rotate in a specific direction with respect to each other, and that forces this product to have one of the alkenes in the benzene being trans rather than cis. And of course you can imagine that this is actually not very possible to form at all. And so that's why under just thermal conditions, the electrocyclic ring opening doesn't really happen or is extraordinarily slow. According to the Woodward-Hoffmann selection rules, we can get the opposite process, the disrotatory ring opening, to happen by switching to photochemical conditions. And indeed, shining light on duobenzene lets you do the 4-electron disrotatory process, and that quickly happens to get to the actual benzene molecule. So this is kind of a cool example just of how highly unstable species can still exist because they don't have a pathway to something more stable. Another point I just want to bring up here is that sometimes people will ask, well, why did this reaction up here happen at all if you told us that it's a very slow process? Well, we have to remember that even in the complete absence of light, there is still some energy around, some probability that the electron in one of the duobenzenes here might get promoted to the higher energy state, and it's that higher energy state that's able to do this process. So in the tiny percentage of the time that does happen, that's how we get the formation of benzene without any light present. That was a look at electrocyclic reactions. We looked at how there are different ways to do these reactions in terms of whether the ends are reacting conrotatorily or disrotatorily. We also looked at the Woodward-Hoffmann selection rules that explain why those processes have to happen either conrotatory or disrotatory. And finally, we also talked about how there is a little bit of torcal selectivity in a ring opening reaction that tries to avoid any sort of large steric interference when doing the rotation